let's get started, ladies and gentlemen. Lesson 1-4, and we're also going to continue on to 1-5. This one is powers and exponents. Let's start with some vocabulary. A power is an expression written with an exponent and a base. So this whole thing down here, right, this is all 4 to the third power. That's the whole thing, is the power. The base is the number that is used as the factor. So in this one, the base is 4. Right? The exponent tells how many times to use the base as a factor. Now I'm going to go ahead and move on to the next slide. Remember, you can always pause the video if you need more time to write down the definitions. In this problem, you're just going to write the power represented by the geometric model. This is a cube, and since volume is length times width times height, we're going to take each of those dimensions, which in this case are all m's, and then we're going to write it with the exponent instead. Since there's 3 m's, that would be m to the third power. Let's do a few examples here of simplifying each expression. -5 to the third power, so we're going to take -5. I like to actually write them out because then I don't accidentally do 5 times 3, right? Or -5 times 3. This way I know that I'm going to get my -5 times -5 is positive 25. I'm going to multiply that by -25, by -5, excuse me, and we get -125. Notice that we raised a negative number to an odd power there. That's going to come up again later. Now in this problem, -2 to the fourth power, it's a little tricky because there's no parentheses around the -2. And exponents only belong to what they're right next door to. So this fourth power really only belongs to the 2, not to the negative sign. We can actually think of this as -1 times 2 to the fourth power, which would be -1 times 2 times 2 times 2 times 2. And all of those 2's multiply out to be 16, and then we multiply by the -1. So we actually end up getting -16 for the answer. So be really careful on those ones that have parentheses versus no parentheses when the number is negative. One of the other things you're going to be asked to do on the assignment for this lesson, the problem set, will be to figure out what exponent you put, right, to go with a specific base to get a certain value. So if we have the number 32 and we want to write that with a base 2, you're going to think to yourself, 2 to what power is 32? And really the easiest way to do this is just sort of a little bit of guess and check. So you think to yourself, let's see, 2 squared is 4, and we know that 2 to the fourth was already 16, right? And so it turns out that 2 to the fifth equals 32. 10,000 with base, writing it with base 10, right? So we go through and we think to ourselves, let's say 10 squared is 100, 10 cubed is 1,000, and we start to remember that little rule, right? That the exponent is the same as the number of zeros after the 1, right? So that means that it's going to be 10 to the fourth that equals 10,000. So writing it as a power, you'd write base 10 raised to the fourth power. Okay. Don't forget about those exponent rules. They're really properties. Any number raised to the first power is itself, and any number raised to the 0 power is 1. Really, any number. 573,246 raised to the 0 power, it would still be 1. Okay. On your Know It page, it asks you to complete a chart on this topic about what happens when you raise positive numbers to different powers and what happens when you raise negative powers to, or negative numbers to even powers and odd powers. So I want you to pause it here and read through this, fill in the chart in your Know It notebook with the examples, and then figure out what the sign of your answers are. I'm going to keep going, but you should pause it here so that you can read through this and fill in your Know It notebook. Last thing, just a quick word problem. In case of a school closing, the PTO president calls 3 families. Each of these families calls 3 other families, and so on. how many families are called on the fourth round of calls. So we could do this with the tree diagram, but we could also just do it with multiplication, right? So each of the first 3 families, right, calls another 3 families, and then everybody calls another 3 families and another 3 families. So that would be 3 to the 4th power, and then we can go ahead and multiply all that out. That was 9 times 9, which is 81. And we can change over to the magic eraser here on our board. And let's see if we have the right answer. 3 to the 4th power equals 81. Okay. Time to move on. That was such a short lesson, I decided to cram in lesson 1-5 onto the same video. So we're going to just keep going here. Lesson 1-5 is a little bit longer, so if you need to stop and come back later, go ahead. Roots and irrational numbers. That's the title of this topic, right? And you already know a fair amount about square roots. Okay, so square roots, most of you are pretty familiar with these, so go ahead and read through this slide on your own. I think you probably have a definition to fill out on your Know It notebook. The principal square root is the positive one. The negative square root is the negative one. We put the negative sign out in front because we can't actually take the square root of a negative number, because there'd be no way for us to get that number by multiplying 2 negative numbers together. Right? If you want both square roots, the positive and the negative, you use a plus or minus sign out front. We're generally mostly concerned with the principal or positive square root. Perfect squares. A whole list of them there. You should have those pretty well memorized. That little number off to the side, it's called the index. We don't use it on a square root. It's assumed to be a 2. On other ones, though, like cube root and 4th root and things like that, you would actually write the little tiny 3 or 4. A number that we raise to the 3rd power to form a product, right? We can go backwards and take the cube root to find that again. So we use the square root symbol, but with a little 3 to tell us it's a cube root. Since 2 to the 3rd power equals 8, that would mean that the cube root of 8 is 2. So we're thinking what 3 numbers times each other would give us 8. And those 3 numbers all have to be the same thing, right? So the only thing that works there is 2. Same thing for 4th roots, right? Except that we're looking now for 4 numbers that we would multiply together to get our final number. So in this case, we were looking for those 4 numbers to multiply together and be 16, right? It happens to be 2's again, right? So we would say the 4th root of 16 is 2. Now you have a whole bunch of definitions. You've done these for the last couple years. Write pretty brief definitions down. Right? Natural numbers, those are the counting ones, starting with 1. I always call those the kindergarten numbers. Whole numbers, just add on the 0. Okay. Integers, negative and positive counting numbers is another way to think of them. Remember, you can always pause this if you need more time. Rational numbers, those are the ones that can be written as a fraction, a over b. So they're all the fractions and any decimals that could result from fractions, which are terminating decimals and repeating decimals. Terminating decimals end, right? Repeating decimals keep going and going and going and going. You can write yourself shorter definitions that like basically what's in the black rather than all of the blue for these. Okay. Irrational numbers, not surprisingly, they're the ones that aren't rational. They're not terminating decimals. They're not repeating decimals. They just go on and on forever without any real pattern. Everybody's favorite one, of course, is pi. Anytime we take the square root of a number that isn't a perfect square, we get an irrational number. So square root of 3, square root of 10, those are all irrational. They go on and on forever. No repeating pattern. Okay. You have a Venn diagram like this in your Know It notes. Looks pretty similar, except it uses circles instead of all rectangles. Right. I like to use this because it helps me figure out where everything goes. So rational numbers, those are things like 4/5, 1.2, 1.3, repeating, anything like that. And it does also include everything else that's inside of it. So all these other boxes, the yellow and the green and the blue, those are also rational numbers. The next category in would be integers. Right. And those are our whole counting numbers and the opposites, so the negative ones and the positive ones. Within that, we have whole numbers, and those are numbers starting with 0, just the counting numbers. And we're going to change pen color so we can actually see it. At the very inner part, we have natural numbers, and those are the ones that start with 1. So if a number is a natural number, it's also a whole number, and it's also an integer, and it's also a rational number. So if you think about putting your finger or your pen in that box, the most describes it. It also fits the boxes that are outside of it, except crossing the line into the irrational. So if something is whole, right, then it's also natural. I think I said that backwards before. So wherever you put your pen, right, that you can often go in, but you can't always go out. Okay, so you gotta watch it. It helps to go ahead and put your finger or your pen in the most specific place you can for that number, and then you can figure out from there. So if I had the number, negative 67, that's an integer, and it's also a rational. So it fits the most specific box and the one outside of it. Irrational numbers, right? Those don't fit with any of the rest of them. If it's irrational, it's not in any other category. Okay. Numbers like that. You're going to be asked to categorize some, and we'll do more of these in class. Okay. So here's a couple examples for you to look at in case there's any of these to do in your Know It notebook, which I think there are. They're going to ask you to put a few in the right places. And I think that's the end.